Last section from chapter 5, we're doing the law of cosines. Looks like I'm going to do it twice. So the law of cosines, first we're going to think about it as a variation of the Pythagorean theorem. So the Pythagorean theorem says the hypotenuse squared equals the sum of the squares of the legs, right? So this is the picture that we get. We use this when we have a right triangle. When this angle theta is 90 degrees, the hypotenuse, the opposite side of the angle, that's C, and the legs of the triangle are A and B. And the Pythagorean theorem says C squared equals A squared plus B squared. Okay, so the law of cosines, the way you want to think about this is that it's a tweak, a riff on the Pythagorean theorem. So the law of cosine is going to say if this angle theta is not 90 degrees, then C squared will be equal to A squared plus B squared with this little adjustment that you have to make. And maybe it doesn't look so little, it does clutter up the formula, but that is the adjustment that you have to make. So what that says is that we'll be able to apply this Pythagorean theorem-like theorem to triangles that are no longer right triangles. So we'll be able to apply it to this situation, for example. So again, it'll be this kind of, now it's kind of a fake hypotenuse. I don't think we should call it a hypotenuse because that's not a 90-degree angle anymore, but the C squared will be A squared plus B squared, but we'll have to subtract off twice A, B cosine of the angle. Okay, and for what it's worth, just when you see this chart here, if the cosine gets bigger than 90, all right, so, or I guess I'm in this third row first. When the cosine is bigger than 90, I'm sorry, when the angle is bigger than 90, the cosine is negative, and that means that this 2AB cosine will be a negative. And if you look at the formula, we're subtracting off a negative 2AB. So it says, in fact, we will be adding a positive quantity. I'm sorry if the algebra got confused there, but that says that the C, in fact, will have to be a little bit longer than it was in the Pythagorean theorem, which looks right by the picture. And if the angle goes to less than 90 degrees, then this 2AB term is positive, and that means we're subtracting off something from the Pythagorean theorem value for C, and that looks right as well. For what it's worth, I won't quiz you on this. You just have to make a note of the formula. You need to subtract off 2AB cosine theta as an adjustment. Okay, so here it is, law of cosines again. I'm just redoing it for this kind of standard picture we have of our triangles, where capital A, B, and C are the angles, little a, b, and c are the sides opposite the angles. So we can apply this formula to any of the angles, and if you apply it to angle A, what you need to think about, again, is that the opposite side is sort of the fake hypotenuse. So you're going to start out with, A squared is equal to B squared plus C squared, but then you need to make the adjustment, right? So you're going to subtract off twice the product of the legs, and the fake legs here are B and C, and then times the cosine of the angle in between, whichever angle you're choosing to use. All right, just one more, I won't do all three, but if you were going to treat B as the angle, then the kind of fake hypotenuse would be B squared, and that would equal A squared plus C squared. Those are the legs being squared, but now we need to subtract off twice the product of the kind of the fake legs minus the cosine of that included angle. Okay, so as mentioned last time, a law of cosines will allow us to solve for these other triangles. This is a situation where we have two sides and an included angle. We know the angle in between the two sides. Law of sines doesn't cover this. For law of sines, we know an angle. An angle opposite one of the sides. Here, the angle. Not speaking clearly here. Here the angle that we know is in between the two sides. We don't know the side length across from the angle. That's the whole point of this. Okay, so the question is then, what is this length of the... So there's a word problem in the book. There's a tunnel going underneath the mountain, and we do some survey where we're able to make these measurements. I want to know the length of the tunnel. That is the length of AB. Okay, so we're going to apply the law of cosines. We treat 82.4 as our angle. That means it's not a 90-degree angle, but we're going to kind of think that it is. That means this is playing the hypotenuse, the opposite side there. I think I'm going to call that C because it's opposite angle C. So the formula would be C squared is equal to the squares of the two legs, but now we need to subtract off twice the product of those two legs times the cosine of the angle in between. Easy peasy. All right, so give that as the exact formula, and then we'll go to a decimal here as well. I'll just ask my machine to do that for me. The cosine of 82.4. Jam all that together. Ooh, that doesn't look right. Oh, sorry, yeah, certainly I've blown this. Well, fortunately can recover. That's the value for C squared. The actual length then, we need to take the square root. It's amazing, that turned out to be at least round to a whole number. Alright, so, I don't know, this turned out 416.809 feet. Okay, so a nice application of law of cosines. The tweak of the Pythagorean theorem. All right, the other situation that the law of cosines allows us to solve is for a triangle when we've been given all three sides. And if you remember just the code here, when we're asked to solve a triangle, it means find the remaining sides and angles. Well, here we've been given all three sides, so the chore here is simply to find the three angles. So we can use any one of the three angles that we choose in the law of cosines. Maybe I'll choose angle C. So if I focus on angle C as being kind of the fake 90, then 12 would be my fake hypotenuse. So 12 squared will be 8 squared plus 5 squared, but then I need to subtract off twice. 8 times 5 times the cosine of the angle C. Okay, so we'll try to solve that for... I'm going to try to do some of these out here. This is 144 equals 64 plus 25 plus 4. No, I'm sorry, this is minus 40 minus 80 cosine C. And now I'll just try to get some help from my calculator. I need to subtract 64 and 25 to the other side. This would be minus 80 cosine C. Maybe I should leave these breadcrumbs here. And now I'm going to divide through by negative 80. So I get cosine C equals 55 over negative 80. And we'll actually work that out as a decimal. Negative, oh, I said it was going to be a decimal, but it wasn't. Give it to me as a fraction. Here it is as a decimal. Okay, so that's the cosine of C. So to get the angle itself, we're going to have to go to a calculator. So C itself, we're going to use the inverse cosine function of negative. I've really got to get this programmed to do this more quickly with my computer. Again, the inverse trig functions on my computer are called arc instead of inverse. Arc cosine is the inverse. And once again, I need to switch into convert to degrees. So in degrees, and hopefully your calculator will bear this out if you're in degree mode, angle C is 133.433 degrees. Okay, so at this point you have two options. One, repeat law of cosines on the other, on angles B and A. Two, we can switch to law of sines. Generally speaking, I find it easier to switch over to law of sines. So because we now know the angle at C, we can use law of sines to get the remaining two angles. Okay, so if you remember, the sine of C divided by 12 will equal the sine of B divided by 8. Right, so we can write that out. I'm going with 2. Going with 2. I was going to type cosine, but this is law of sines now. So sine of C divided by C should equal sine of, I'll do it in symbols first. Oh shoot, sorry. And then plug in. So law of cosines allowed us to figure out this angle C. We were given this was 12. Sine of B is what we're going for now. Sorry, it scrolled off page. The little b was 8. Okay, so that does in fact allow us to solve for sine of B. It winds up being 8 sine 133.433 over 12. Right. Same requirement here to get the angle B itself. We're going to need to do some calculator work. We need to get a decimal here for sine of B, and then I'll take the inverse sine of B. Sorry, we need to take the inverse sine of 0.48 to get B. I don't think I said that right. So sine inverse of 0.484119. And I don't think I'm going to do the third one. I'll let you decide which method you would like to use for that. 180 pi. And by third, I mean the angle A. Oh, what am I saying? Yeah, there's a good point here. Now that we have two of the angles, we would be on a fool's errand to use law of cosines or law of sines, either one, to get the third angle. Remember, the third angle should always be coming to you essentially for free. So angle C, wait, no, angle A was the last one, is 180 minus B minus C. So that's definitely the best way to get that last angle. 28.9548. And as a final answer, then we have solved the triangle. We were given the three sides and we've been able to find all three angles. Okay. Oh, timestamp. Oh, 15. It'll be short today, I think. So we've got we've got a couple of formulas for areas of a triangle, but here's a third one that's very handy when you know the side lengths of all three, when you know the lengths of all three sides of the triangle. If that's the information you are given, this is the easiest way to get the area. It's not the only way, because as we've seen, if you've been given the three sides, the law of cosines can tell you an angle, and then knowing two sides and the included angle, you can work out a formula for the triangle that way. But the Heron's formula is definitely the way to go here. If we add up the three side lengths, that's going all the way around the triangle, that's called the perimeter. I'm labeling that with P for perimeter. If we take half of that, I guess that's called the semi-perimeter, but I've labeled it S to maybe try to go with that name, semi-perimeter, half the perimeter. Then we can write down the formula for the area in terms of this S and the side lengths. So it's the square root of S minus A, S minus B, S minus C as a product. Right, let's put it in action. And I don't know if we'll do the proof. Maybe I'll just put the proof on screen. Okay, so yeah, so this is the triangle that I think that we were just working with. And again, after we found an angle, we would have more than one way to compute the area. But let's just do it using Heron's formula. So the perimeter, we go all the way around. Let's start with A, B plus C. That's 25. Oh, why did they have to make it an odd number? That's just, because now the semi-perimeter is going to be not a whole number. Oh, so be it. Okay, so then here comes the Heron's formula, which you'll definitely want to have on a note card. It's the square root of 12.5, 12.5 minus 5, 12.5 minus 8, and 12.5 minus 12. Hopefully I got all that typed in right. And going to a calculator for this. One more try. Come on, there we go. Boom. This triangle has area 14.5237. Okay. The proof idea, really, I'm just going to leave it on screen for a second, but it comes from the formula that we already know for a triangle, half the product of sides times the sine of the angle in between. Again, something that should be on your note card. We're going to rewrite sine in terms of cosine using this formula that we've seen before. It does get a little involved because now we're going to have to use the law of cosines to solve for cosine in terms of the side lengths. And when you make this final substitution, then it's just a bunch of shaking the bottle until the formula pops up. It's just algebra that takes place after that. Okay, so what that's worth. All right, the last topic for the day then is simply, now that you know both of these, law of sines and law of cosines, how do you tell which one to use? And this is what I would put on a note card. I would say for law of cosines, you need two sides and the included angle. Kind of like the Pythagorean theorem is what you should be thinking about. Or you need all three sides. Okay, so just kind of keep that in mind for law of cosines. And then if you don't have that, you're going to be using law of sines. Okay, so we could list what those are, but just say otherwise you use law of sines. Okay, so let's look at a couple of triangles and try to decide, are we using law of sines or law of cosines? Okay, so I'm looking for sides. In this first example, problem number 23, I'm only given one side. So this is not law of cosines. So it must be law of sines. That's what you're going to use to find x. Problem 24, all three sides, boom, boom, boom. You're going to use law of cosines. All right. Let's try one more. And I guess to find the theta, apparently. One more here. Yeah, so problem number 21, we're only given one side. Yeah, so exactly as we said before, we're only given one side here. So that will be law of sines. I'm just blanking on law of sines for just a moment here. In order to use the law of sines, we're first going to have to compute the third angle for free, the 180 minus these two angles. That'll give us the angle at B, and then we can get the law of sines going. For problem number 22, this time we have two sides. And we have the included angle. The angle in between the two sides. And that's the other situation where we're going to use the law of cosines. So here we'll be using 40 degrees as kind of the fake 90. The x squared is going to be the fake hypotenuse. I'm just typing this out real quick. And the little adjustment that we'll have to make, or not so little here, but and that equation will allow us to solve for x. All right, that's the law of cosines.